Hi, calculus kids. Well, this is getting old, right? I also, for my 6th period, I won't see you tomorrow either because I have to go to a stupid meeting. So, but tomorrow will be our practice day, and we will have our Unit 6 test on Friday. And remember, for the test on Friday, it's all no calculator, and it is just integration, integration, integration. The vast majority of the problems are going to be from integration 1 through 5, which is from your quizzes, which I'll have back for you tomorrow. Even period 6, I'll have the sub give your quizzes back to you. Then, of course, there's integration by parts, and then what we're doing today, which is integration by partial fractions. So tomorrow will be practice, and I have a worksheet for you with 50 problems. I know, cry. But these kind of problems really do just take doing them over and over again. So 50 practice problems, where about 3/4 of them are from integration by parts. From integrations 1 through 5, and then about 1/4 of the problems are these last two integration techniques, integration by parts and integration by partial fractions, and that models the AP exam. The vast majority of the integration problems that you'll do without a calculator on the AP exam are really not even going to be integration 1 through 5, they're going to be integration 1 through 4. There are some problems, the topics, the integration on integration 5, integration by parts, and integration by partial fractions are tested, just not a lot, not heavily. Alright, so for this warm-up, I chose this one because, especially after just teaching tabular integration by parts, students are so tempted to choose x to the 4th, and they're like, oh, cool, I'm going to make my table, right? Here's f of x, here's g of x. X to the 4th is awesome because I know I can get do the derivatives all the way down to 0. But remember, to do tabular integration, it was true that the first function had to be something whose derivative went to 0, but the second function, or the second factor, I had to be able to integrate easily. Well, you don't know how to anti-differentiate ln2x. Well, let me just say that there's no formula for it, right? I showed you that to integrate ln, you need integration by parts. That is not easily done. So my first instinct was not correct. Now, if I saw x to the 4th with a sine or cosine, or an x to the 4th with an e to the x, then I would think tabular integration. But with this, remember, when I see a product, and I can't unproduct it, and I can't find a formula for it, I think integration by parts. And when I think integration by parts, I use my Lippitt guideline as my choice for u. And what is the very first choice? That's right, L, for logs. So ln2x is my u, and x to the 4th dx is my dv. The derivative of ln2x is easy, right? 1 over 2x chain rule times 2 dx, which of course is then just 1 over x dx. dv is x to the 4th, so remember its antiderivative is not 4x cubed, is it? It's 1/5 x to the 5th. So the integral of ln2x, which is u, times x to the 4th dx, the integral of u dv is, by proof, equal to u times v, which I'm going to put in the front, minus the integral of v du. And then of course this integrand reduces to what? X to the 4th. So its antiderivative is x to the 5th over 5. And of course I could factor in x to the 5th and from the numerator and a 5 from the denominator and write that out, which I would, and write it that way, which of course I would only do to match multiple choice. So remember, when I see a product, can I unproduct it? Can I match a formula? If I can't, I think integration by parts, and then I think Lipit. Then I will decide if I need tabular or solving for the unknown integral. Right? I do this first. Alright, so that is, again, integration by parts. I kind of think of this in most instances as undoing the product rule. Now I have to think about a quotient. So just like with integration by parts, when I see a quotient, the first thing I think is it a formula or can I undo it? Right? And when I can't, I cry. When I get over crying, I say to myself, I remember pre-cal. Oops, sorry, didn't mean to go. Right? Fortunately, my pre-cal teacher, who I didn't love at the time, I now love my pre-cal teacher for teaching me how to break up fractions into multiple parts. I have to think for AP, my denominators are going to be either degree 1 or degree 2, and as a matter of fact I think AP has started to focus just on degree 1. Now I want to remind you from elementary school. In elementary school, when you first learned about fractions, you learned firstly you couldn't add fractions unless they had a common denominator. So let's pretend my common denominator was a 5, and my first numerator was a 2, and my second numerator was a 7. I certainly didn't make this 10, right? My common denominator was 5. If you have 2 out of 5 plus 7 out of 5, you actually have how many out of 5? Now you usually just write 9, but isn't it true that that's 2 plus 7 over 5, right? Now let me remind you about something else. What if you had 2/5 plus 4/7? You knew you couldn't add those until you changed them, right? You had to multiply this by a 7, which meant you had to multiply that by a 7. You had to multiply this denominator by a 5, which meant you had to multiply the numerator by a 5, so that you were multiplying both of the fractions by a 1. Then what did you have over here? You had 7 times 5, and your numerator was 7 times 2 plus 4 times 5. Partial fractions is taking what you learned in elementary school and breaking it back up. Right? Taking this fraction, which of course looked like 14 plus 20, which is what, 34? Right? 14 plus 20. Right? Can you go from 34 over 35 all the way back to the original 2/5 plus 4/7? That's what's at the heart of breaking up a fraction into its multiple parts, right? Taking 34 over 35 and breaking it up into its parts. So, here's my example. The first thing when I look at that is say to myself, oh, maybe that's u substitution, right? So I say, oh, u must be x squared minus 2x minus 3. du is 2x minus 2. Oh, I can factor that, right? That's 2 times x minus 1, so 1/2 du is equal to x minus 1. So I'm just going to make this to the first, and then somehow I've got to take 5x minus 3. No. Cry. Mad cry. That doesn't work. But I thought of it first. I try to avoid partial fractions if I can. Alright. So, I can't use u substitution. I can't do integration by parts either. It's not a product, right? I mean, I could turn it into a product to the -1. That's not helpful. That's integration by parts. U substitution's already in it. No, no. Cry. So, I do look at the denominator and remember from Algebra 1 that I know how to factor that. And when I factor it, my factors are degree 1. Notice I've dropped the calculus. Drop calculus for now. No calculus. Let's do pre-cal. So I say to myself, I can break this into multiple parts. Yay! So I say, I know that one of the denominators was x minus 3 and one of the denominators was x minus 1. Right? Again, think of this as like, if this denominator was a 7 and this denominator was a 5, what's the common denominator? 7 times 5. But I don't know. I put this a and b up here because I don't know. It's not like I can say this is 5x and this is minus 3, right? Take a second to convince yourself why that's not true. Now, here's a really powerful statement. What's on the left is equal to what's on the right. Now it is important that the linear factors are not repeating. Right? That makes the partial fractions a little hairier, which again I think you took care of in pre-cal. For now we're not going to worry about that. But I do know that those two numerators have to eventually be 5x minus 3. So since I have an equal sign, I can multiply by whatever I want. So I'm going to multiply through by the common denominator to kill my fractions. Right? I mean, if you need, I'm going to multiply this side by x minus 3 times x plus 1, which means bam, bam. I'm going to multiply this by x minus 3 times x minus 1, this term. Kill that denominator. I'm going to multiply this term because I'm following the rules of algebra. Whatever you do to one side of the equation, you must do to the other side. Bam, bam. And I'm left with an equation with no denominators. Now, here's something that you might not think of until somebody tells you. If I have an equal sign, it means that when I solve for whatever x I use, has to make these equations equal. I can test whatever x I want, right? I distributed my a and my b, and then I set like terms to one another. So again, if you have an equal sign here, 5x is on the left, therefore anything with an x on the right has to equal 5x. And everything without an x on the right has to eventually get to a -3. This becomes a very simple solving for two equations with two unknowns. Now, I'm going through this kind of quickly because I'm going to show you a faster way to do this. But if you forget the faster way, this way always works. Right? And this is just algebra. This is not even pre-cal, this part. Right? Once I get here, when I have two equations with two unknowns, that's algebra 1. Right? Well, at least algebra 1 when I took algebra 1, or when I used to teach algebra 1. Not anymore. Anyhow, notice now, once pre-cal is done, pre-cal in algebra 1 is done, now I'm going to put the calculus back. So now I put my integral and my dx back, but what is the integral of a sum? The integral of a sum is the sum of the separate integrals, right? Wow. Now I know I popped that answer out real quick, but let me show you what I did. Where can I do this where I've got some more room? So how I did this was the 3 times the integral of 1 over x minus 3 plus 2 times the integral of 1 over x plus 1. U for this one u is x minus 3, du is dx. For this one, u is x plus 1, and du is equal to dx. So this is 1 over u, du. And what is the antiderivative of 1 over u? It's ln of u. Absolute valued. And I do need the absolute value signs because x minus 3 is the linear function that has ranges that are both positive and negative, and the same with x plus 1. Oh my god, and of course my plus c. This technique is called integration by partial fractions. So here's the shortcut. The shortcut is called the heave-aside method, which I think is funny. Well, firstly, it was developed by an English engineer, so of course engineers are like, I am so over this solving two equations for two unknowns every time. Also, I think it's pretty funny that his name is heave-aside. I don't know how to pronounce it, but that's how I like it, heave-aside, because I'm going to heave aside that algebra 1. My kids like that joke. Womp womp. So notice step 1 is the same, right? I drop the calculus, right? Drop the calculus from now and just do pre-cal. I am going to do partial fractions. I have an equation. I'm going to multiply through by the common denominator. I like to call this the annihilation method. That's what I think of, right? And I think about Arnold, the Terminator, the annihilation method. And I didn't make up the annihilation method, but I did link it to Arnold. I wonder if I should tell Arnold Schwarzenegger that every year I teach a calculus method in his name. I mean, Oliver Heaviside is dead, so he won't care. And Arnold, he might be pretty pleased about that. Anyhow, I am multiplying by the common denominator. Now, remember because I have an equal sign, and I have what's on the left is equal to what's on the right, and I have these x's, right? And this is all linear stuff, so the domain is all real numbers. Well, of all the real numbers in all the world, in all the universe, how about I decide to let x equal -1 and see what happens? Do you see why Arnold is here? What happens when you let x be -1? Now that means you have to put -1 here, -1 here, and -1 there. So 5 times -1 is -5, minus 3 is -8. A is terminated, and I'm just left with B, and -1 times minus 3 is -4. Boom! What do you think I'm going to do now? It terminated A so I could get B. What am I going to do now? Bam! What happens when you let x be 3? That means I have to put 3 here, 3 here, and pow! 3 there. Bye-bye, B. Notice I get A and B without having to do Algebra 1. I mean, I guess you could make the claim that I'm doing Algebra 1 by solving a one-step equation, right? But I heave aside the solving 2 equations with 2 unknowns. Once I've done that, remember I go back to calculus, I put my integral back, I separate it into 2 integrals, I do my u substitution, and of course I get the same answer. Crazy! Let's practice. Factor the denominator. Drop the calculus. Did you like that? Break it into parts. Now, of course, if you had 3 factors, guess what you would do? Yep. Plus c over the other factor. You just pray I don't do that to you, right? Multiply by the common denominator to kill the fractions. Wow, this is a pretty violent lesson, isn't it? Now, you could use the heave-aside method, or you could use Arnold the Terminator. What do you want to let x be? I chose -2 first. Bam! Bye-bye, A. Then I chose 0 next. Bam! Bye-bye, B. Once I have A and B, whee! Put the calculus back. Osmosis those 1/2 out. The integral of a difference is the difference of the integrals. Done and done. I love Arnold. What's your thoughts on the Terminator movies? I saw Terminator 2 before I saw Terminator 1, and I love Terminator 2. Terminator 1 was a good backstory. The rest of them, no. Alright. This looks nastier. Wait a second. Wait just a second. I want you to go back. What in example 2, what's true about the relationship of the degree of the numerator and the degree of the degree of the denominator? How about example 1? Uh-oh, I'm starting to get worried. The degree of the numerator compared to the degree of the denominator. Uh-oh. What about this one? If the degree of the numerator is equal to or higher than the degree of the denominator, you guys are the worst. Use long division first. Oh, there's pre-cal again, coming back to bite you in the butt. Actually, I taught a number of you how to do long division in Algebra 2. Come on now. So, first I have to get myself to a partial fraction where my numerator, degree of my numerator, is smaller, right? In order to use partial fractions, the numerator degree must be less than, not equal to, less than the denominator degree. That's not the case here. There's a lot of crying in this lesson too. So fortunately I took Algebra 2 and Pre-Cal and I paid attention. What do I multiply x squared by to get 2x? And you know what? Synthetic division doesn't work here. Don't need it. I don't need to find zeros. I just need to divide. 2x, right? Gets me 2x cubed minus 4x squared minus 6x. Now I don't know about you, but I do not like to subtract. So when I can, I choose to add the opposite. Since now this is degree 1 and I'm dividing by degree 2, I know I can stop. I also taught you what to do with the remainders, right? Just like when you divide what? 4 into 25, right? You get 6 with a remainder of 1. Well, what does that mean? That's 6 and 1 out of 4, right? You have 1 remaining out of the divisor 4. So how do you write this? 2x and 5x minus 3 over x squared minus 2x minus 3. This red expression is equal to 2x cubed minus 4x squared minus x minus 3 over x squared minus 2x minus 3. Just like 6 and 1/4 is the same thing as 25 over 4, right? Those are the same. I can't use partial fractions this way. Partial fractions cannot be used, but since this expression is equal to here, I can use partial fractions right here. And I don't need partial fractions right here. This is just regular, right? So here's all this written a little nicer. Take a moment to appreciate the planning of your teacher and notice that that problem was example 1. Wah, wah. So that's how I could break up, right? There's my partial fractions from example 1. So finally, I get back to calculus. So I had a degree in the numerator that was too high for partial fractions. So I did long division, got myself to an equivalent expression, and then I have an equivalent integral of a sum, which of course is the sum of all the integrals. So the integral of 2x plus the integral of 3 over x minus 3 plus the integral of 2 over x plus 1. Now remember this 3 and this 2, and this 2 I will all osmosis out front. The antiderivative of 2x, of course, is just x squared over 2. 2x squared over 2. And then this is the answer from, this is the part from example 1. This is the part of your answer that if you don't recognize this, if you don't recognize, uh-oh, I can't use partial fractions, you just start breaking it up now. Firstly, your partial fraction work is going to be nastier. Secondly, you will get this part out of it. You will. But you will miss this. If you don't divide first, you won't get this part of the answer. So, again, here's an example where you have to recognize, there's a lot of things that you have to recognize. First, you have to say, crap, I have a quotient. Then you have to say, can I unquotient this? Does things factor and cancel? Is U substitution something to do? And then once you run through all your options and realize that you have to do partial fractions, you then have to look at your degree here and realize, crap, since the degrees, since the numerator degree equals the denominator degree, you must do long division before partial fractions. What do you multiply x squared by to get 5x squared? Fortunately, this is not a devastating problem, right? I like to add the opposite. Right now I have a degree 1 with a degree 2 that I'm dividing by. So therefore, this expression is the same as 5 plus my remainder on top of what I was dividing by, which means I'm integrating 5 dx, which is easy peasy, plus integrating 2x plus 9 over factor That's what I'm going to do partial fractions on. So I'm going to drop the calculus and go up here and say that 2x plus 9 is equal to, I don't know, plus I don't know, multiply through by the common denominator to get one equation without any whoops, sorry. Bring Arnold to the situation. Let x equals -2 means a is gone. Oops. Forgot to put -2 here, didn't I? Bring Arnold again. Come back down here. Fill in, there's my a over 1 over x minus 3 minus 1 the integral of 5, and remember that's x to the 0, is 5x. Woohoo! And again, up here, what happens if I forgot and I don't divide and I just do my partial fractions work? You will get all of this. You will lose your linear term. Alright, so partial fractions does get worse when you have scenarios like repeated factors or, God forbid, cubics and stuff like that. AP is not interested in that level of pre-cal work on a calculus test. They just don't have the time for it. So we focus here on just what AP is going to give you. Of course, when you take calculus for real in college, your algebra is going to get even nastier. You have that to look forward to. Yay! All right, kids. So again, I will have your quizzes back for you tomorrow, and 50 problems for review for you to practice. But work on the partial fraction homework tonight, and I will see most of you tomorrow.